Good evening, I am Amitoj and I'll be presenting on the topic solving PDs using Fourier neural operators as a part of the course project of PFC 351 Fundamentals of AI/ML. What this topic is about is solving partial differential equations using a deep learning method called Fourier neural operators. Now, there have been many instances of solving partial differential equations earlier as well. Most of them usually use numerical methods such as finite difference methods or finite element methods. But the problem with most of these methods is that they do not scale really well because the data is very high dimensional. Like the grid sizes that we use for solving any partial differential equation, they usually scale up a lot. For solving any 3D equation or any 2D equation as well, you need very high computational resources to do anything meaningful with that. So, what we are essentially trying to do here is we are trying to use deep learning as a faster solver than the traditional numerical solvers that we used to earlier have. Now, I'll be briefly going through what exactly is the meaning of solving a partial differential equation and what an operator is. So, we can consider Darcy partial differential equations, for instance. So which is minus divergence A gradient U is equal to F. So what U here is the temperature or the pressure over some domain. So let us say this is my domain. This may be some region inside a room or somewhere where I am mapping my temperature or I'm mapping my pressure. And F here is the source field that I'm given over this entire domain. A is some constant, which is the conductance or permeability. It might be the same for the entire region, or as in this case, A is also varying in the entire domain. And what we finally have to do is, given this A, which is varying over this domain, we have to find the corresponding U. And this is my input function, and this is my output function. So, like a function maps any vector from like it maps a single vector to another single vector. So it is a mapping between one vector space to another vector space. Similarly, an operator is a mapping between a function space to another function space. So in basically what it is that A here is a function that I'm using, and the operator that I'm applying on A is G. So there must be some transformation that will be existing from A which will allow me to go to U. So going from A to U is done by this operator G, which acts on this function A and gives me the output function U. So my main goal is to learn this operator G. Now, I'll not be using the Darcy partial differential equations for this project. Will be mainly focused on the Navier-Stokes equations. Now, the Navier-Stokes equation are a set of partial differential equations which govern the motion of a fluid inside any, let's say, container or in the air. So it is very essential to solve it. For instance, if I'm designing any airfoil, or I am seeing how heat is flowing inside a room or inside some engine, I have to model it. So it is extremely essential to use the Navier-Stokes equation and efficiently solve it. But these are nonlinear equations, and solving them requires very high computational resources and very good accuracy to model it. So what I'll be showing this architecture called Fourier neural operators as a new paradigm to solving uh, these complicated partial differential equations. So, as I previously covered, in principle, an operator will map a function to another function. So this is my input function and this is my output function. Now, let's say this is the domain where this is the x-axis and this is the y-axis, and we are given the values like a heat map in this instance over this entire domain. No, but for feeding it into some computer, I'll obviously have to discretize my domain because I can only store finite number of values. So as it is written here that in practice both inputs and outputs are discrete. So this is my input domain and this is my output domain, and these are just different ways of discretizing the input and output spaces. So what this is using here is a Sobolev space, and this is a better method of discretization. Like this is a better representation of the input, and this will give another better representation of the output. but it is usually easier to deal with uniform discretization than Sobolev space discretization. Because as you can imagine, doing all of this, like finding the Sobolev points in a 3D domain, will be very difficult. So it is usually best to have a uniform discretization. But what happens with a uniform discretization is that the points become extremely large. Like if this is a 10 cross 10 grid, these are 100 points. As soon as I include a 10 cross 10 cross 10 grid, it becomes 1,000 points. Now, similarly, if my grid was discretized to 100 points, which is a very fair enough number to capture the input function effectively, then in that case, my total number of points will be 100 cross 100 cross 100, which is a million. So these usually scale a lot as soon as I add another dimension. So as it is said that there is only a discrete operation possible on the digital computers that we have. So we need to operate in the discrete space, but there is a problem with operating in the discrete space. That is that there are multiple discrete representations which are possible. So as we can see here, we used a uniform discretization scheme for this and a Sobolev space discretization scheme from this. I could have used a simple discretization here where the distance between these points became larger and larger as it approached one boundary, or smaller, or any other function I could have used to describe the discretization scheme. So if I am using any deep learning method for this, the problem that I get, and even for any traditional solver, is that due to the multiple discrete representations, there is no notion of a continuous to discrete equivalence. If I use traditional deep learning for this, what will happen is that my neural network will learn a very simple discrete representation learning. So it will learn how to go from this representation to this representation, but this essentially is the same problem. Going from this input to this output is essentially the same problem. But because the discretization scheme has changed, it will not be able to accurately map to this output. So there needs to be some proper notion of continuous to discrete equivalence that we need to somehow instill in our model. So this is the Navier-Stokes equation that I will be using. So the Navier-Stokes equation is actually a set of three partial differential equations, which includes the x component of velocity, y component of velocity, and z component of velocity. And but we usually condense it into a single partial differential equation by defining the vorticity. Now, if my u is the velocity vector, I can take its curl and define another vector known as the vorticity, which can be defined as this, its x, y, and z components. And using them, I can derive the vorticity equation. This is for the z component. And I will be only using one single component of the vorticity for ease in calculation and the ease in availability of data set that I found. So yeah, this was the supervised learning of some target L with deep neural networks. So this is how traditional deep learning would handle it, is that this would be my source. So this would be my discretized input space, and I have flattened it into a vector, or I could have used the simple 2D space and used a 2D convolutional network for it. So what is happening is that these layers, which are simply matrices, are being multiplied to my input, and these are the non-linearities that I'm including here. I've included a simple sigmoid. It could be a ReLU or it could be a tanh as well. A ReLU is always preferred. And so this is basically what is happening at some kth hidden layer, that my output z of k plus 1 is simply the nonlinearity multiplied by this ck into zk. Zk is the input that I'm giving to my kth layer, which is simply the weight matrix multiplied by zk plus the bias vector. And these are the parameters that I will have to find, wk and pk. And finally, the output that I will get via this neural network operation, I will be comparing it with the ground truth, and I will be able to optimize it using any optimizer. Mostly I will be dealing with the Adam optimizer, and I'll find the optimal weights that will minimize this loss function right here. And using this, I will be able to find an optimal neural network. But there was another problem that we found. So this is again exactly what I showed in the previous slide, is that we have this input vorticity and it has been discretized into this grid. So as you can see, it's a huge grid in 2D, and it will be extremely large if this was a 3D representation. and then I'll be learning some operator G star, which lets me go from input vorticity to the output vorticity. So this is exactly what I'm doing. I'm doing uniform sampling, then I'm applying a convolutional neural network, and then I'm interpolating it to find the output function space. But the problem that we found in this was that the CNN is not learning anything concrete. It is not learning the actual operator. What it instead doing is that it is learning some a discrete representation of my input. So if my training resolution was 64, that is these number of points were 8 cross 8, then my CNN was trained on this and it performed really well. It gave only 5% as the test error. But as soon as I changed my sampling scheme, so let us say I went from maybe reduced the number of sampling points, or even if I increased them, in both cases my error increased. So what this indicates is that it has not actually learned anything about the physics of the physical system that I have here. All it has learned is going from one discrete representation to another discrete representation. But what I really want my model to learn is to effectively go from the one function to another, no matter how I sample it or no matter how I discretize it. And why is this important? Because most of the times I won't be having any uniform sampling scheme. Let us say if I'm having some data of airflow over an aircraft, then most of the times it will not be in a uniform sampling scheme. Some data points will have, let's say, 64 cross 64 discretization scheme, and some other one will have 128 cross 128 discretization scheme. So what I want is my model to perform well for both of them, because I expect it to learn the actual physics, not just going from one vector to another vector. So this is where this notion of neural operators kicks in. So what operator learning is in general is that I have this abstract partial differential equation, so which is going from u to f, and it is parameterized by this operator d. So my solution operator is going from this x function space to y function space, or more formally it is a Banach space, and my operator g will take in a and f and give me the output u. Now, as we just discussed earlier, that parameterizations do not generalize well over all the other sampling schemes that I may use. So we need to put in some notion of continuous discrete equivalence in our model, and that was achieved exactly by neural operators. So neural operators was something which was formalized in this paper by Kovacsky et al. In 2021. So what it is basically doing, the essence of it is that as neural networks expect discrete inputs, let's say like a vector, what I want to do it, what I want to do is generalize it to infinite dimensions. So for instance, deep neural networks are using these layers, which are discrete matrices, finite sizes, and a single hidden layer is basically doing this operation, which is all happening with finite sized inputs. Now, a neural operator will generalize these deep neural networks to infinite dimensions. So basically, rather than going from one vector space to another, it is going from one function space to another function space. And I need to find the function space versions of the bias vector in that case, the weight matrix, and the activation function that I use. So I have pasted this slide that I wrote on my tablet. Uh, so what a neural operator essentially is doing is it is having these neural layers right here. These are not weight matrices in the general sense. The mathematics of it is a bit different. So it is mathematically defined as rather than taking a multiplication. So for instance, this AK was being multiplied by Y using a matrix multiplication. What I'm generalizing it to is an integral over this over the entire input space that I'm getting, and this is the kernel that I'm getting at the nth layer, which is kl x comma y, which is multiplied by v of y dy, and I'm adding this another function for defined for the kth layer. Just a second. Yeah. And I'm again adding some nonlinearity in the end. And what this x is that I can basically change my x and get the output function at the desired x that I want. Now again, of course, as I have to feed this all in a computer, I will have to discretize v again by using all these points. So v, xi, I1 to n, these are my point values. I've discretized it on n points. Now, during training or during testing, especially, I can change this n, but essentially my model will not face very large deviations from the test error that it earlier got. So again, I approximate this integral using the quadrature rule, and using the quadrature rule, this can turn into a summation, and this wj will be 1 over n. So this is basically averaging over, this will be like 1 over n into klxi yi into vyi and plus blxi. So this is essentially the computation that I will be doing for a neural operator, and this will go for all I1 to n. Now there is a slight problem that even simple neural operators face, and that problem is the computational complexity of it. So the computational complexity is O of n square, which is quite okayish for, let's say, a 10 cross 10 grid. But as soon as you scale it to a 100 cross 100 grid, or a 100 cross 100 cross 100 grid in the case of 3D, this computational complexity blows up. So what would be a better alternative? It would be to have it O n log n. Like that is the best that we can do. So what Fourier neural operators do is in essence going from O of n square to O of n log n. And what is the motivation that we can get, like why are exactly we going into the Fourier space, is that just remembering the fact that a fast Fourier transform takes O n log n time. So we can somehow gain some motivation as to why we even want to venture into the Fourier space domain. And this is exactly the reason why Fourier neural operators were developed. So this FNO was proposed by Lee et al. In 2020. Now what it is essentially is replacing the continuous kernel that we had here with a translationally invariant kernel. Now there were two motivations why they did this. The first motivation was of having some translational invariant kernel. Now what a translational invariant kernel is, that no matter what the x or y is, the output will only depend on the relative distance between them. And this makes a lot of sense because for instance, this patch right here evolved into something like this, for instance. Now if this patch, rather than being here, was in the middle, this patch should also shift in the middle. So, or if this patch went right into the top right corner, this sort of arc that you're seeing here should also shift towards the top right, because the physics aspect does not depend on where you imaged it, right? I could have put my camera a little bit below and this part would have been above in the image. So this is exactly the motivation as to why they're using a translationally invariant kernel, is that k of x comma y, which is k of x minus y, just encodes the relative distance aspect. And the kernel integral operator then, when as soon as I replace k of x comma y with k of x minus y, becomes the very famous convolution. So this basically becomes a convolution in the kernel k and the input v. So what we're essentially doing is a convolution, but in Fourier space. Now why are we even including the Fourier space? Because this convolution will become very easy. The first instant, the first motivation that I have is that the convolution becomes quite easy to handle. It simply becomes a multiplication in the Fourier space. And the second main motivation that I have for going into the Fourier space is resolution invariance. So no matter what represent discretizations I work on, there will be absolutely no effect on the Fourier transforms that I get, until unless I of course cross the Nyquist frequency. But for most general use cases, no matter what the discretization scheme I am using, or no matter what the step size is, the Fourier content remains the same. It does not depend on the resolution that I'm using. So hence Fourier transforms are resolution invariant. So these two things, making the kernel translationally invariant and then very cleverly making this the convolution and applying it in Fourier space, automatically solves the resolution invariance problem as well. So what essentially it becomes is that I've replaced the bias vector by the bias function, and this again is the exact same thing that happened in the neural operators, in the simple case of neural operators. uh, Now this part right over here, this part that I'm using al into y, is replaced by taking the Fourier transform of k into the Fourier transform of v, and then taking the inverse Fourier transform after it. Now, as you know, taking the Fourier transform and then taking the inverse will do nothing. But the good part is that doing the computation and calculating the k and v matrices in the Fourier space rather than the spatial space helps make them resolutionally invariant. So this is exactly what I've written, that parameterize the kernel in Fourier space, and we can implement it also very fast using FFT. So because FFT has the complexity of O n log n. So this is essentially what my layer looks like, that I take A of x, pass it through some matrix P. Then I have this Fourier layer right here, which takes the Fourier transform. You get all these Fourier modes. Then you retain only the top energy Fourier modes, because that is where the main content is. You approximate it. And then you again take the inverse Fourier transform and you multiply by some weight matrix as well. This is like a skip connection that we take motivation from the ResNet to use. So this is like a residual connection that I'm using. So this of course improves the back propagation when I'm doing it. And finally I pass it through some nonlinearity. So this essentially is my Fourier layer. I've written the maths of it on the slide. That this part has been discretized, sorry, this part has been replaced by a translationally invariant kernel, and then we again take the convolution. And this is essentially, I have just shown an example of what uh, taking the Fourier transform essentially means. So this will be better explained in this slide. It's written much more clearly, that just taking the Fourier transform in the K space from X space involves writing the function as a continuous summation of some basis functions psi. And these basis functions here are of course the complex exponentials. And then I can again transform back to the spatial space using the inverse Fourier transform. So as I said here, that the Fourier transform of K convolution with V is f of k into f of V, and then I can take the inverse Fourier transform of it. And the computational complexity scales as O n log n, because I'll be doing all these operations using a fast Fourier transform. So this is essentially the maths of what a Fourier neural operator is. Now I will be demonstrating the code that I have run on the Navier-Stokes equations for vorticity, and I'll be explaining why this method works really well. So this is the data that I am using. This data is by Zenodo, and I have uploaded this data on the folder that I will be sharing. And so basically, first we just download the data into this zip file, and then I have converted this zip file, and this is how my data looks like. So I have a lot of samples. I have around 1024 samples, uh, and basically the shape of each image that I have is 128 cross 128, and I have 1000 to 1024, some like some number in between. I have some samples for both in distributions and out distributions. What in and out distributions essentially mean is that I have two types of distributions. Out distribution is a little shifted version of the in distribution. So I will be testing my trained neural Fourier neural operator on that as well, to see how well it generalizes the physics of it. So yeah, essentially this is my input size, which is 1020. I have 1024 samples of 128 cross 128 images. These are my input images, which is my initial vorticity, and this is the final field that I will be getting. Again, a 128 cross 128 image. Now I'll be showing how one of these images looks like. So this is one of the in distribution Navier-Stokes fields. So what this magnitude here essentially is the vorticity. So wherever the color is high, it has high vorticity, and wherever the color is a bit dark, it has a low vorticity. So essentially, I have to learn a mapping from going from one Navier-Stokes fields to how it evolves with time. So what I can just show you what I mean by this. So this is my input. Like this was the initial condition that I started with. After some time, it evolved into this vorticity right here. So this is my ground truth, and this is the prediction that I will be trying to do with my model. So I have already run this cell because it took quite a lot of time, and as you can see, it is quite close to it. Not exactly, but still, it is essentially capturing the essence of this ground truth quite effectively. Like you can see the dark patches, where the dark patches are already are actually present as well in the ground truth, and you can see this notion of the light color changing into the yellowish color at the bottom, and this yellowish scheme that you are seeing right here. So it has essentially very well captured the from the ground truth to go to the prediction. So I'll be explaining what I have exactly done here. So I defined my input and output tensors, and I essentially after that defined my Fourier neural operator model. Now I have taken these Fourier layers I have implemented using the NeuralOps library. This was a very good paper that was released some years back. And what this includes is it includes the basic building blocks, the neural layers for building many of the neural operators that are possible. Maybe convolutional neural operator or a like a unit neural operator, any of that, even a spectral neural operator. You can implement all of these using the NeuralOp library. So I've implemented a Fourier neural operator using this. So essentially, what I've done here is I've defined these layers. Now n modes 16 comma 16 means that I will be retaining only the top 16 modes in the Fourier space. I'll be discarding the others. And finally, I've used the Adam optimizer here, and I have trained it for 50 epochs. And finally, the loss that I will be calculating is the relative L2 error, and I've stored it as ftrained.pt in my notebook. So as you can see right here that after the training has been done, my relative L2 error that I'm getting is 0.1503, which is quite less. And of course, you can see it by the prediction and the ground truth as well. Now, this is okay. Even a convolutional neural network can do that. The main test of the Fourier neural operator is if it does not shoot its error value for other resolutions that I will be using. So I have generalized it later to other resolutions as well. Uh, so this is the magnitude spectrum that I finally got, and this is actually not of a lot of importance for what I am about to do here. This was just for seeing if there is no aliasing or anything like that. Um, so I tested it on the relative, I calculated the relative L2 error on the out data as well, which is 0.2348. As you can see, it is not a very huge increase as we saw in the case of a convolutional neural network. It went from 0.15 to 0.23 from the in distribution to the out distribution. So this is what the out distribution looks like. So yeah, as you can see, it is able to somehow match even these predictions quite well. Now, it is not able to match this arc quite well, but still it is able to capture a good enough essence of the ground truth. So this is the power of Fourier neural operators that we see over convolutional neural networks for learning the physics of any physical system. Now, I have again tested it multiple times on many of the data, like both the input distributions and both the output distributions, and it is able to capture the physics of it quite well. Um, Now, after this, the main thing that I had to test was downscaling the data as well. So I have downscaled my data from 128 cross 120 to 64 cross 64. Now, if it is able to provide me a good relative error, like a low enough relative error on the 64 cross 64 data as well, although the model was trained on 128 cross 128. So this earlier model that we saw uh, right here, this model was trained on a 128 cross 128 resolution. Whereas now I will be testing this model on 64 cross 64 in distribution and 64 cross 64 out distribution. We have seen that it performed well on 128 cross 128 out distribution as well, but it might not perform well on 64 cross 64 in and out distributions. But we'll see that is not the case, and the FNO performs well on that as well. So uh, yeah, so as you can see, I first of all trained the model on a 64 cross 64 resolution, and it is still quite close to the ground truth that I got, and the relative L2 error I got is only 0.15 in this case. And again, I tested this model on the high resolution, and the relative error is even lower, surprisingly, which is 0.099 only. So you can see it is generalizing really well. And I have even tested the earlier high resolution trained model on the low input data, and you can see that the error is only 0.1546. So you can see that the model, when it was tested on 128 cross 128, was giving an error of 0.15. And again, when testing that model on the low input data, uh, In the case of a CNN, it should have given a high error, but it still maintains its accuracy to 0.1546. So this demonstrates how the model that we have trained is resolutionally invariant. And again, training it on low resolution data and testing it on high resolution data, doing the inverse, still gives me a good enough accuracy and even much better than expected. That is 0.0994. So this, and we can compare these findings to a convolutional neural network which does not perform that well. So here I have in the final cell trained a convolutional neural network, and as you can see finally that the relative L2 error that I got on the 128 cross 128 resolution, the resolution that I used during training, is 38%. While evaluating the same model on a 64 cross 64 test image, that is 73%. So it really shoots up, and it really matches this graph that we saw, that the training resolution is only relevant when you are testing on the same resolution. As soon as you shift from the one testing resolution to another, the error will shoot up significantly, which was not in the case of a Fourier neural operator. So this essentially shows how Fourier neural operators can be used to solve many of the problems. And one of the most interesting use cases might be in solving the Schrodinger equation, as evolving just solving the exponential e to the iht, where the Hamiltonian is quite large, is usually very difficult to compute. Now, these methods can capture the time evolution and the dynamics of any quantum system really accurately, and these are being actively explored in the fields of quantum computing as well, to explore the dynamics of any qubit under noise. So this was it from my side. Thank you.